we learned about 5 pairwise equivalent formal representations of regular languages. They are TFA, NFA, NFA with epsilon transitions, regular grammar and regular expressions. And later we shall see one more representation which is a kind of equivalence relation representing regular languages. And before that we shall see some limitations of regular languages. We shall ask a question: are all languages regular, or can we find a language which is non-regular? The agenda for this lecture is to look at a language and see whether that language is regular or not. So today we shall see non-regularity of languages, or in particular we will see a language which is non-regular. First we can try to answer this question: is this language a regular language which is n number of a's followed by n number of b's for all values of n greater than or equal to 0. When n becomes 0, epsilon is the string that you are getting. When n becomes 1, it is AB. When n becomes 2, it is AABB or A square B square. Likewise it goes. So we need to see whether this language is regular or not. So what do you think? Is this a regular language? Suppose the answer is yes, it should be the answer. Then, without loss of generality, we can say that there exists a non-deterministic finite state automaton A for n. We can try to construct an NFA for this language. So if you look at this NFA, it is accepting epsilon, which is in the language. We can try to extend it. Now we need to accept AB, and now we can see that this NFA is accepting epsilon and the string AB. Which is the next string to be accepted? It is A square B square. A square B square. Now these are the only 3 strings accepted by this NFA. Now go for AQ, BQ. You can easily verify that this is the language now. Now you can go for A raised to 4, B raised to 4. Likewise you can get an NFA. Now is this an NFA? Yes, it looks like an NFA. And here you can see that the state 1 represents the fact that till now one A is processed. So after this, if you just process a B, you can accept. Number 2 state represents that till now 2 A's. So after that 2 B's can be accepted. Similarly here 3 and 4, likewise it goes. And you can observe that this logic requires infinitely many states. For each value of n here, there is a separate state at least, and there are in fact more. So this logic requires infinitely many states, and hence it is not a finite state automaton because there are infinitely many states. So this is not going to work. Now the question is, is there a clever design for an N of A which requires only finitely many states? Maybe there exists one, we may not be able to find it, but there could be an N of A which can manage the language in a clever way. So, how will you say that there is no such N of A, or how will you find that N of A? It is a difficult question to answer. And before we answer this question, let us look at this question about a graph. What is the question? What is the length of the longest acyclic path in a graph with n vertices? We can try to look at simple graphs and generalize. So, we will see a graph with only one vertex. You cannot have an edge, right? If you have an edge, it will create a cycle. So, the longest acyclic path is of length 0. And if you look at a graph with two vertices, the longest path is of length 1. If you add one more edge, it will create a cycle. Let us go for a 3 vertex graph. The maximum length of an acyclic path is 2. If you add one more edge, then definitely it is going to create a cycle wherever you add it. Maybe you can add as a self loop or from one vertex to other. In whatever way you add, it will create a cycle. And in fact, you can generalize and say, if there are n vertices in a graph, then the longest acyclic path can have a length n minus 1. So, is it correct? It looks like it is correct, and we can in fact prove using the principle of mathematical induction that the length of the longest acyclic path in a graph with n vertices is n minus 1. We cannot have an acyclic path of length more than n minus 1. We are going to prove this by applying induction on n, where n is the length of the n is the number of vertices in the graph. For the induction base, you take the number of vertices as 1. So, just one vertex in the graph, and so no edge is possible, and hence the path length is 1 minus 1, which is 0. Now, the induction hypothesis. Assume that this statement is true in a graph with curved vertices. So, the hypothesis tells us that in a graph with curved vertices, the longest acyclic path can have a maximum length of k minus 1. Suppose this is the longest acyclic path in the graph with curved vertices. So, the length is k minus 1. Now, the induction step. For the induction step, you try adding one vertex to this graph. Note that from the induction hypothesis, the longest acyclic path is of length k minus 1. Now, if you put this edge, you can easily see that you are getting a path of length k. Already there is a k minus 1 length path, plus this edge will give you a length k path. So, this is the k minus 1 length path plus one edge. Okay, no doubt that we are getting a length k path when the number of vertices is k plus 1. Now, the question is, can we have a length k plus 1 path? Then the statement is not correct. So, can you have a length k plus 1 path? What do you think? So my question is, can you extend it further? Maybe you find a vertex in this graph itself and you extend that path like this. Now the length could be, this is k minus 1 plus 1 k plus 1 k plus 1. Is it possible? If this is possible, then the statement is wrong. We will prove that it is not possible. Why? Because then why don't you have a k plus 1, length k path in the graph with only k vertices? If this is possible, why don't you extend it like this? It is not possible because the hypothesis tells us that k minus 1 is the length of the longest path. So you cannot have this edge. Why? Because if you put that edge, then it is going to create a cycle somehow. Maybe this is that cycle it is going to create, and that is why you don't have this edge, and hence the maximum length of a cyclic path is k minus 1. I hope you are getting me. Then we can actually get a cycle in the new graph like this. See, we said it was not possible because it will form a cycle. Then of course we have a cycle now forming like this. This is a cycle. So you cannot have this edge, and hence the maximum length acyclic path is only having length k, and hence we are proving the statement. Okay, and this is a very crucial result that we can utilize to prove the regularity of the language for which we wanted to prove whether the language is regular or not. So the graph theoretic result that we just proved is that in any graph with n vertices, the length of the longest acyclic path is n minus 1. Or in other words, if you look at a path of length n or more, then definitely there must be a cycle in the path. And this is the observation that we will be utilizing now to prove the non-regularity of a language. We are going to use that result to prove that this language is non-regular. Proof is by contradiction. So for the purpose of contradiction, assume that this language is regular. The moment you assume that it is regular, then without loss of generality, assume that there exists a DFA A such that the language of A is this language, and that is why it is regular. Now let A power m, B power m be an input to this DFA such that the value of m is greater than or equal to the number of states in the DFA. Okay, you can have any natural number here. So of course you will get a value m such that m is greater than or equal to the number of states in the DFA, which is a crucial point to get the proof. And definitely this must be accepted because this is in the language m number of A's followed by m number of B's. So it must be accepted, and now suppose this is the accepting path for A to the power m, B to the power m. Okay. Now if you look at this path, there are m simples in the path. So m edges are going to be there in this path. So the length of this path is m, which is greater than or equal to the number of states in the DFA. Then from the previous result we know that this path must contain a cycle. Not that it is only A's, each edge is having the label A. So you can write this path as, because this is there is a cycle, I am going to represent it with a cycle like this. So we have m number of A's and we are splitting now m as I, j and k, so that m is nothing but sum of I, j and k. Okay, suppose m is 100, I am saying that okay, maybe this is some 50 number of A's coming here, then some 10 number of A's is coming like this back to the state again, and 40 number of A's are going like this. Just like that I can divide. The fact is that there is a cycle. Now we have enough things to get the contradiction. Now you can say that a to the power I, b to the power k, b to the power, sorry, a to the power I, b to the, a to the power k, b to the power m is in the language because you have an accepting path. Without traversing this loop, if you go, you will get a to the power I, a to the power k and b to the power m. So no doubt. That means, what is this a to the power I and followed by a to the power k? That is I plus k number of A's, that is it. Here I number of A's followed by k number of A's. So in total a to the power I plus k number of A's followed by m number of B's in the language. Now you can see that what is I plus k? If from this formula, if you obtain I plus k, it is nothing but m minus j. And what is j? J is the length of this path. Okay, j is the length of this path. And now actually this is not in the language, but you are accepting it. Why is it not in the language? Because here the number of A's is less than the number of B's, because j cannot be equal to 0, because there is a loop like this, and thus we are getting a contradiction, and therefore the existence of DFA for this language is an assumption which is a wrong assumption, and thus we proved that this language is non-regular. I hope you got the proof. Otherwise, please watch this lecture again and see how we did this proof. So today we proved that the language a to the power n, b to the power n, where n is a natural number, is not a regular language. Basically because finite state automaton is not having memory for counting the number of A's, so that it can be matched with the number of B's. But a finite amount of information can be remembered in the states of a finite state automaton, but for this language we need infinite counting, and hence the language is not regular. We have utilized a non-result about graph theory to get a contradiction for the assumption that there exists a DFA for accepting this language. In the next class, we shall learn about a necessary condition for regularity called pumping lemma, which can be used to prove that certain languages are non-regular. Thank you.